a bit because this is where we get very cosy. No, it's okay. Right, what those police officers were listening to was this. That's not Morse, that's Bordeaux code. In fact, this is the replica of the equipment. Well, this is actually the equipment, some of the equipment they were using. The problem with Bordeaux code is that we can't immediately do anything with it. We have to put it through another machine, which is this machine, which is called an undulator. And this produces a paper tape printout. Now you can see that on the top of there you've got the undulator tape, which is given as a trace, and you'll see below a punched tape. I'd like to pass those around. We set up a special station at Knockholt in Kent to listen to these messages. And we had people here who could identify from the undulator tape what those characters were. They could read that. And the really good ladies that we had reading those could read those anything up to 60 characters a minute, which is some going. They would then produce a punched tape from that, which we could access further. But I said earlier that what we were looking for, or what Colonel John Tiltman was looking for, was a way of breaking that. Because on its own, it's unbreakable. And if you want to know why it's unbreakable, again refer to the videos that I mentioned, because there is one video that covers Lorenz and Bordeaux code on its own. Bordeaux code on itself, in itself, is unbreakable. That's the beauty of the system. However, there was one German operator, we think it was on the Athens to Vienna link of the High Command, had a message to send, all 4,000 characters of it. We reckoned it probably took him the best part of an hour to send this. So he sent it, sat back for a rest, message came back down the line, words to the effect of, sorry, didn't quite get all of that, please send again. Now the one thing you don't do is send a message twice on the same settings. Here we have a German operator who's probably been told that this machine that he's using, and this was it, the Lorenz SZ41 or 42, is the most complex piece of equipment in the world. It's totally unbreakable. It's got 12 rotors. Around each rotor there are a whole series of switches, 501 in total. So he thinks to himself, well, it's unbreakable, 12 rotors, 501 switches, forget it. He sets the machine back to its original setting that he used to send the first message. Mistake number 1. Mistake number 2. The first word that he sent on the message, the first word that came out of any of these messages, was Spruck Nummer, message number. The first time he sent it in full. The second time he got as far as Spruck N and realised he could abbreviate number to NR, which he did. And then he abbreviated the rest of the message wherever he could. Knockholt intercepted these two messages. And what they found was two messages with exactly the same indicator, because like Enigma, the Lorenz operators had to send an indicator first to tell the recipient how to reset his machine. The first 7 letters, or first 7 characters of each message were exactly the same, the coded version of Spruck N. And the second message was 500 characters shorter. They knew this was important. They didn't know what the messages meant, but they knew it was important. Get it straight up to Bletchley Park. And of course, John Tiltman got his hands on these. He took one look at those messages and knew exactly what the operator had done. This was his heaven-sent opportunity. So using his own mathematical skills, over a period of 2 weeks, he completely extracted the string of obscuring characters that had been used to code those two messages. Again, if you want to know what obscuring characters are, refer to the videos. And that string of obscuring characters was called a key. But we had nobody at the park here who knew what to do with it. But shortly afterwards, we got a new guy joined the research section. His name was Bill Tutt. He was actually a chemistry graduate, but he had one abiding passion in life, and that was statistical mathematics. So the head of research gave him the key, gave him the 2 messages, and said, let's see what you can do with this. So he went away. 2 months later, he came back and he said, well, I can't tell you what the machine's called, can't tell you what it looks like, can't tell you who makes it, but we can tell you how it works. Because what Bill Tutt and his team had done was to work out statistically that this machine, whatever it was called, had 12 wheels. One bank of 5, which we call the K wheels. These K wheels worked independently and incrementally. A second bank of 5 called the S wheels. These all moved together, sometimes moved, sometimes didn't. And 2 small wheels, which we call the M wheels, or the drive wheels. They also worked out that the K wheels introduced one obscuring character to code the message, the S wheels introduced a second obscuring character, and the 2 M wheels were the pin wheels or the drive wheels. In fact, what Bill Tutt and his team did was to work out the entire logic of Lorenz, which was quite amazing because we never even saw a Lorenz machine here at the park until the end of the war. So we had now a means of breaking the messages. The problem is that it could take up to 6 weeks using paper and pencil to work it out, by which time that message was probably dead and buried, long gone. We needed electromechanical means to break it. So it was suggested that they went down, in fact it was Max Newman, who was one of the great mathematicians here, went down to the post office research station at Dollis Hill, just outside of London, talked to them, told them what the problem was, and what they came up with was this. Now, we didn't know that Lorenz was called Lorenz. We didn't know what it looked like. We didn't know anything about it. So we called it Tunny. We codenamed it Tunny. And all the messages that were produced by Tunny, we called fish codes. So what this was essentially our own Tunny machine. It was, in fact, a Tunny emulator. The Tunny machine has got 12 rotors and a whole number of switches around each rotor, which determines the pattern of that wheel. And those switches, the position of those switches, determine which obscuring characters are introduced into the code to code the message. So you see on here 24 rows of plug sockets in 12 pairs. The top pair we can plug up to represent the patterns on the wheels, the switch positions, and the bottom row in each pair we can plug up with that wheel's start position. Once we've plugged up all 12, we can switch the machine on, and it's obviously not switched on. I don't know anything about this machine, so I'm not going to touch it. But you can switch it on, start, reset, no, right, okay. What this thing does is it what's called initializers. And all of these set themselves to exactly the same position that the Lorenz rotors were to form the coded message that we have got to decode. Now there's one problem here. In order to plug this up, we've got to know what the wheel positions and the start position was, what the wheel patterns and the start position was. Now to get that information, again, we could work it out from the message using Bill Tutt's methodology, but it could take us, as I've said, anything up to 6 weeks, by which time it was dead and buried. So Max Newman worked out a mathematical model from Bill Tutt's methodology that would do that. So he went down to the telecommunications research establishment at Malvern in Worcestershire, and he talked to a very bright electronics guy there called Charles Wynne Williams, who came up with a design for this. It was originally designed as the Robinson machine, but those of you who know anything about wartime cartoon characters, when this came up to Bletchley Park, the operators took one look at it and said, that's not Robinson, that's Heath Robinson. And it looked a bit like Heath Robinson. It basically worked on 2 paper tapes. One tape had the original message, the coded message, punched up, formed into a loop. The second tape had on it a punch tape which had some of the wheel patterns and start positions which we'd worked out quite laboriously to begin with. The two tapes had a common start point and a common stop point. We had a reading head, we had a whole selection of valves, uniselector switches and a readout. This is actually being rebuilt at the moment, so we don't have the reading head in position yet. But the reading head was designed by a man called Dr. Arnold Lynch. And the idea of the machine was you would start the two tapes from a common position. They would then go through the machine and be read by the reading head. And using what was called double delta cross-correlation, the machine teased out of those two data streams the pattern and the position for the first Lorenz wheel, for the first K wheel. Once it had done that, we stopped the machine and put the two tapes one character out of register and then ran them through again, and the machine did exactly the same thing, teasing out the patterns and the position for the second Lorenz wheel. And we did that until we had all 5 K wheels, the first 5 K wheels. Once we had those, we could work out the rest quite quickly, longhand. But the problem with Robinson, well, there were several problems. The tape feed was friction. So of course the tapes kept slipping and going out of register, so you had to stop, re-register, start again. Being paper tapes, they would stretch very slightly. One tape relative to the other. Went out of register, stop it, restart. Sometimes a tape would break, so a new tape had to be punched up. It was relatively slow. It was only reading characters at 1,000 per second. And there was no printout. It used a readout, so it relied on 2 operators standing there in front of the readout, scribbling like mad as figures flashed in front of them, an ideal way to make mistakes. But when it did work, it proved that Max Newman's mathematics were absolutely correct. But what we needed was something a lot quicker, a lot more reliable, a lot faster. And at this point, Alan Turing said to Max Newman, why don't you go down to Post Office Research again? There's a guy there, brilliant electronics engineer, his name's Tommy Flowers. Why don't you talk to him, see what he can come up with? So Max Newman did. He went down, he talked to Tommy Flowers, he explained what the problem was, he explained the mathematics behind it. And what Tommy Flowers came up with was actually quite staggering, because he virtually started with a piece of paper. And what he designed was the world's first semi-programmable electronic digital computer. It was called Colossus. We have one here, a rebuild of Colossus, exact replica. It lives next door. That's where we're going now.